physical laboratory. It was at Imperial College for many years, but now National Physical Laboratory is your moniker. And the title of the talk is Non-Destructive Detection of a Single Optical Photon, with cavity-free added at the front.
It's really nice to be asked to give a sign. Is this on? No.
There's a little switch on the top.
Right, that's okay now? Yeah, good. It's nice to be able to talk about a science problem, because normally what happens is I give these sorts of talks and I usually preface quite quickly with one of those where we talk about the money flow, but you've heard all this already from Liam, and we are really close to that, and that's all I'm going to say. But the danger is when you spend a disproportionate amount of your time as a quasi-retired theoretical physicist on these sorts of things, you end up in this sort of situation. Right, so you've read it all. And so that's why when John said, why don't you talk about some physics for a change, I thought this was a great relief. I am becoming more vegetative, but still, never mind. So what I'm going to talk about is some stuff I was doing with Jason Twomley and the group at Macquarie. Jason was my postdoc a million years ago, and we've maintained interaction. Okay, so quantum non-demolition methods, just to remind people about these things, because it's Friday afternoon, we might as well start gentle. If I take the classical measurements, and I can work on canonical variables of position and momentum, and there's no real limitation other than the accuracy of your measurement apparatus to what you can do. And in particular, you know, if you have a meter or a ruler, for example, it doesn't have any effect in any measurable way on the variability of what you're trying to measure. You know, there's no feedback. On the other hand, in quantum mechanics, we know perfectly well that canonical variables are subject to an uncertainty relation. And I quite like the fact that there is this Heisenberg stamp which has the uncertainty relation on. I think it's entirely appropriate that they've got this squiggle sign there, because as those of you who looked at it very carefully know, Heisenberg completely screwed up the uncertainty principle. Okay, there are two uncertainty principles, and in his book on the physical interpretation of quantum mechanics, he confuses them utterly. Okay, one is there's this one, another one is it's this one, and that factor of 2 is critically important because the factor of 2 that comes in there is actually the effect of trying to do a joint measurement. Okay. So if you do it properly in terms of state preparation uncertainties, you get that one. If you then build in the effect of your joint measurement on the uncertainty, you get that one. Okay, so if you do a kind of tomography experiment and look at state preparation, you're exploring this kind of, if you like, the Wigner contours. If you do joint measurement, you're exploring the Q function, the extra noise that comes in, sometimes called Arthur Kelly's noise. And I think it's quite fun to realize how much undergraduates' perception of quantum mechanics has been completely screwed by Heisenberg. All right. So, all right, now what's a non-demolition measurement? So if I've got some variable I'm trying to measure, so I've got a system measurement apparatus coupling, I've got a measurement apparatus, and if you look at the Heisenberg equations for what happens to your some quantum variable for your system, if that measured variable is actually an integral of motion, in other words, its commutator with the Hamiltonian is 0, so as the QS and the system measurement interaction commutator is 0, then you have the opportunity to do a quantum non-demolition measurement. And the applications are profound. You know, you can do ultra-precise measurements, you can mess around with squeezing, you can look at a whole raft of things, and in particular you can look, for example, at single photons, and that's the challenge that I'm going to try and address. Alright, so, quantum non-demolition of photons, single photons. If you stick them in a cavity, it's fairly straightforward to do, and that's what basically underpinned Serge Roche's Nobel Prize. This is Serge in one of his cheerful moods, by the way, if anybody knows him. And using Rydberg atoms with extremely strong coupling constants to microwave fields in a high Q cavity, they worked out exactly how to do this, to do a QND measurement of a cavity field using Rydberg atoms. Okay, it's part of what underpins Serge's Nobel Prize. Another way of doing it in a high Q cavity in an optical regime is to use the James-Cummings Hamiltonian normal mode splittings and so on. And that was the kind of thing that others have done and so on. But very much the pioneer of this was Serge. If you look at other methods for doing this, this is the James-Cummings Hamiltonian in a high Q optical cavity. You look at the splitting of the normal modes, and that will give you the ability to do a QND measurement of the sort that was pioneered very much at the Max Planck in Munich. You can take exactly the same Hamiltonian that Serge Laroche used for Rydberg atoms to drive the cavity fields, translate it into transmons and do exactly the same thing, and that's what Steve Gerwin and Sharkov did with superconducting systems. Exactly the same Hamiltonian. Alright, so what about travelling photons? So what people have been looking at for a very long time is to look at how one field can modify another field through the Kerr effect. Those of you atomic physicists, the Kerr effect is just the Stark effect but applied to the field. Okay? So the cross-Kerr effect, where you've got a coupling between two fields. So one potential Hamiltonian for the cross-Kerr effect is this one, an Ising Hamiltonian, so A dagger A for a probe field, A dagger A for a signal field. That and its ancestors have been looked at for a very long time. Trying to build a Franklin gap with gate was what Jerome Milburn tried to look at back in the 80s. Okay, Philippe Granger has looked at this. Misha Lukin has looked at these kinds of things. And the real challenge on this one is that the nonlinearity that couples them is extremely small. All right. So if you have a go at it, and now Alex Gator and his group have done this, attempted, and what they've got is phase shifts, where a signal passed through a holy fibre, and looking at these kinds of things, they've got 0.3 milliradian per photon responses, relatively fast. Okay. Others have looked at this. This is per Delsing, Jerome Milburn, Tom Stace, a whole raft of other people, again using a transmon system, where what they find is, to be honest, the signal to noise is really a killer for travelling photons. All right. So as a result of that, a couple of people came up with no-go theorems. Okay? In particular, Jeff Shapiro with a no-go theorem with a fantastically provocative title: single photon kernel nonlinearities do not help quantum computation. And then Julio, slightly less provocative, Banner closure, possibility of last phase shifts. And so when you see things like impossible and do not help, it spurred me to think, oh yeah, let's have a go. So we can finish now if you like. Say they're wrong, by the way, and we can have a cup of coffee again. So let me tell you where they're wrong, because it's not impossible and they do help. And the trick is, don't have these things propagating with the same speed as single photon wave packets through the medium. Because if you do, they never meet. Well, if they do meet, it's hardly ever, yeah? So how can they talk to each other? So you don't you can counter propagate. You've got various things you have to do. In any sort of mixing experiment, you need to have energy conservation. Energy conservation in any nonlinear optics gives you entanglement in the spectrum. The entanglement is both what we're interested in and as an obstacle because it limits the fidelity. So what you need to do in order to bypass Jeff Shapiro's no-go theorem is to say, have them moving at different speeds. Just let them travel through each other. And as soon as you do that, either through counter-propagating or moving at different speeds, you find the no-go theorem doesn't apply. All right, so here's the key idea. What I'm going to take is a chi3, a full-wave mixing Hamiltonian, okay, where I've got three fields. Now, I'm perfectly well aware that cubic Hamiltonians are terrible things to play with, okay? But live with it for a bit. Okay, so let's take a system where you've got A dagger B, C, and its conjugate. And what you want to be able to do is to have the ability for these three fields to interact. So if you start with one photon in B and one in C, your time evolution is such that you go, well, you've got 0 there, 1, 1. Then the Hamiltonian generates interaction. You go 1, 0, 0 with an I there. And then the Hamiltonian then takes you 0, 0 and a 1. If you can do that, you can build a phase gate, because you've got this minus sign. And that was proposed for a C phase gate by Langford and company. So what we're going to consider is the fact that the B and C photons have got different speeds, so these wave packets move through each other. Okay? If you assume they co-propagate at exactly the same speed, you get the no-go theorem. Right. So, what we want to do is produce what I'm going to call a Rabi-like interaction. I'll explain why it's Rabi-like in a moment. So here's my Hamiltonian, okay? I said relax, it's not a cubic Hamiltonian, it's really a quartic one, okay? And you can, on the right-hand side, that's what Alex Gator's group did in that fibre I showed you earlier, or you can do a four-way mixing. You can imagine a situation where you do this, for example, in atomic vapor. Okay, so, and we've explored those exactly that kind of atomic configuration for this four-way mixing in detail. Right, but if you look at those sort of Hamiltonians, those quartic ones, what you discover is because of this cross entanglement with the fields, that the fidelity is low simply because of the entanglement. And so again, there are people that have written sensible articles saying this sort of thing looks like it's fraud. So we've still got to overcome that, this co-propagation. So here's our model, and I'm still yet to explain why it's Rabi-like. Okay, it's four-way mixing. I've got a strong pump field, sufficiently strong that I treat it as a classical field. Okay, I've got a signal field, an auxiliary field, doesn't matter what it is, by the way, and my probe field. I'm going to assume the probe field is a weak coherent state if its amplitude is small. Okay, and what I'm going to do is run an evolution which does exactly what the Langford scheme does, to bring me a minus sign in. Okay, so that's my trilinear Hamiltonian, but of course in there is my other field variable. Okay, and that means that I can tune my coupling constant by cranking up the strength of this classical pump. So it's chi3 interaction. Over here we've got a measurement scheme, because what I'm going to look at is that weak coherent state goes through this chi3 medium. I've got a beam splitter. For once I've got the beam splitter in the right orientation. Haven't I, John? He's my beam splitter expert. Okay? If you get a phase change, that turns to that. Okay? And what I can do then is to do a joint detection over on the other side to see what happens. Alright, so why Rabi? Okay? That's Rabi, if no one has ever seen a picture of Rabi. I will take an anecdote for 10 seconds. He was at an atomic physics meeting that I was at. He was the guest of honor at the dinner. He wandered around all his quantum optics stuff and said, I've never worked in quantum optics. What the hell is this Rabi frequency? True story. Anyway, there's Rabi. That's my Hamiltonian. I keep rewriting it with different symbols, but never mind. That's my Hamiltonian. Now, it's a theory session, so everybody knows about Schwinger-coupled bosons, don't they? Yeah, of course you do. Schwinger-coupled bosons, I can represent those field operator products as spin variables. Okay? So I can take A dagger B and its conjugate to be S plus and S minus, which are standard Pauli operators. Okay, if you don't believe me, try it, and you'll find it's got the SU2 algebra underneath. Okay? So if I do that to that Hamiltonian, I get the James Cummings Hamiltonian. Okay? Right, now what I want is for the adventurers of you to try this. It's the Balinese plate dance. Okay? What you've got to do, because it's a fibre bundle. Ah, and I failed. He did it. Right, stand up. It's more agile than me. Rotate. You've got to go through all the way. Right. Halfway through, you got a minus sign. You saw? That's what we're doing. That's the phase gate that you want. Okay? Right, so if we do that and we get the Jones Cummings Hamiltonian, that's what Roche got a Nobel Prize for. But now we've got a pseudo spin, which is just field variables, with a coupling constant that we can manipulate by cranking up the size of the pump field. Okay? Right. Oh, this is a bit wordy. Sorry about this. So what I'm going to do is to start. This auxiliary field plays absolutely no role whatsoever, except somewhere to park stuff. So in the Roche scheme, what you do is to send your excitation amplitude up to this subsidiary state, and then bring it back down again. Okay? So all I'm going to do is to occupy that auxiliary mode, and then bring it back down again to the vacuum state. Okay? So I've got a probe field. Okay, my weak coherent state, I'm going to roughly assume is like 0 plus a little bit of 1. Now I know that's fatal, unless you check it. Okay? You can get spurious entangled if you don't watch out. So I've got a weak coherent field that's nearly no field at all. A little bit of 1. Okay? I run through the evolution of this stuff, and the signal field will drive that transition from 1 photon in that probe field, none in the auxiliary, to none in the pump, and 1 in the auxiliary. Okay? Then you keep it going again, and you'll bring it back to 1 in the pump, 0 in the auxiliary, but as my friend here just demonstrated, you get a minus sign. Okay? And that's all you're going to do. Okay, so my field then is this, with that minus sign in there. Alright. Well, of course you know how to detect it now, because if I have a beam splitter, this thing comes in, and I'll do it with that. By adjusting the strength of that, I get no field at all at this detector. Okay? So if this is unchanged, and I bring this one in, the 2 amplitudes cancel out, and I get a vacuum. If on the other hand I've done that phase shift, okay, and I bring this in, these two add up, and I get twice the amplitude when I detect it. Okay? So if the probe field comes in and changes, and there's no photon in the signal, you don't get anything on the clicks. But if 1 comes in, you get the phase shift, you get twice the amplitude, and you get a click. So it will work. And you put losses in, you can put the Liouvilleans in, you solve it. I don't know quite what happened to that equation. Interesting. That's A sub P, that's alpha sub P there. Okay, so that's the detection when you know you got it right. So if you get a click, you know you get a photon in there. If you get no click, you know there wasn't a signal there. So that's my measurement about whether there was something in there or not. And it was done by non-demolition. It really came all the way through. Okay? The error probability is easy to evaluate, and it's just the exponential of 4 times the phase space difference mod squared. Okay. Well, you'd better not put too big a probe field in, because I had an assumption that it was mainly none and a little bit of 1. Okay? If you crank it up a bit, it's none, a little bit of 1, and a small bit of 2, and then you're stuffed. Okay? So the fidelity gets screwed if your probe field it gets a bit big, but that doesn't matter. And if you look at the Wigner function of this stuff, you put 1 photon in, you get this peculiarly deformed Wigner function, which is the blue bits are non-classicality, and the circles on the right side are what happens if you put a vacuum in. And if you look at the Hallstrom bound for this, it's really pretty good. You know, you've got the fidelity is as close as you want. Right, now, that's all in a cavity. And you say, wait a minute, you're supposed to be talking about travelling fields. So the next thing to do is to say, what about a travelling pulse. So a Gaussian single photon wave packet that rips through this medium. And if you do that for this particular four-way mixing Hamiltonian, you get these absolutely brutal equations to solve. Okay? So I looked at it for quite a long time. I thought, oh, forget it. Let's do a numerical integration, which is what we've done. Okay? In the low occupation number limit, it is possible to actually solve them, I've discovered since. Okay, so you grind them through. The method, there's some references on how to solve such equations for quantum nonlinear optics. Keith Blow and Simon Phoenix actually had the better version of how to do it, and that's the method we used. So a Gaussian wave packets with a width sigma. Okay, you've got that already, haven't you? Yeah, good. Right. So this is the normal ski. This is in the Shapiro limit, where we propagate them together, same speed. And it's only in this tiny middle region that they had any chance whatsoever of talking to each other. And the fidelity is just dreadful. Okay? So being a theorist, you can fiddle around with these things and say, actually, what I can do is actually correlate. I mean, I know this is unphysical. Oh, I should never say that. I don't think it's very physical. It is actually, if I had correlation between the signal and the single photon field and the probe, okay, then you get quite a lot of phase shifting all over the place on that one. Okay, but we'll skip that because it's not. Oh no, I actually like it because you get this little swimming animal. I think it's lovely. There you go. as they move past each other. Okay, but this is the. Oh come on! There you go. That's the more realistic situation, where you get a pi phase shift, high fidelity. The pulses that are going aren't correlated, and all I've done is fiddled around with the delay time between the two, so they move past each other. All right, running out of time, I know. So there you go, a disproof of the no-go theorem of Shapiro. Okay, and I showed this to Julio and his postdoc. And they said, no, you can't be right. There's a no-go theorem. And after they ground it out, they said, you are right. Okay? So, repentance. As a result, we must conclude the earlier work by one of us was in error. Okay, jolly good. Right, so some conclusions. There ain't a no-go theorem for this stuff. You can do it. Okay, if you want to make gates out of this stuff, by the way, it's a fearsome prospect for an experimentalist, because I've assumed the propagation speeds are different. Okay, and you want to put this on a chip. You think, wait a minute. So John's already turned off and he's looking at a book or something. You might be able to use birefringence to do that if you wanted in some way. But what it does mean is that you can, I think it's nice to be able to disprove no-go theorems in general. So firstly, you can get high fidelity in this, you can get your pi phase shift. The coupling constant is tunable, it just depends on the amplitude of the external field, and I think it's doable. And I could imagine a situation where you could take a holy fibre or a capillary and fill it with stuff. You can even use slow light techniques to actually increase the propagation time. I think it's worth a go. Thank you for listening.
The papers and the questions.
Thank you very much. That was a very entertaining talk. So, do you see applications of this kind of, detecting the photons without actually destroying it to, new types of detector architecture?
Yeah, of course there are, but I haven't thought of any of them. But my challenge was just, Jeff Shapiro is a really good friend, And I just thought this was a really great way of winding him up. But when you do any sort of disproof like that, there are things that come up that are possible. But we haven't really. We just want to see somebody have a go at it experimentally. So we have a program grant. Me, Music, Kim at Imperial, Ian Walmsley, not quite at Imperial, Josh Nunn, I think really is at Bath, and others, and we're going to have a crack at it. And for reasons that escape me, we've called our program grant Narcos, which means we're on Homeland Security's hit list now, I'm sure. And we will have a go at it because we're looking at at single photon stuff in terms of supremacy stuff. So we're going to now fiddle around with a bit of nonlinearity en route. So we'll have a play with it. But at the moment, we're still in the playing game, really seriously. I wouldn't want to sell this to the Chancellor of the Exchequer.
Other questions?
If getting to, if the problem is like getting these two guys to be at different speeds, could you have them counter-propagating at the same speed? It's like that.
Yeah, if you do that, you've got to worry about the non-locality of the susceptibility that goes into those integral differential equations. We did that, it does work, but then you have to work out exactly what sort of genuine nonlinearity generates that kernel function. So we've done a bit of work on it, but what we haven't done is mapped it onto what we know about true susceptibilities.
I had one question in the sense that other people have sort of looked at these ideas of, say, reversing the exponential decay of a photon and coupling it efficiently to cavities and things like that. So there are other people have sort of done things or even bringing two top hat photons together in an ideal the non-local medium. Then the top, as long as they're overlapped.
That's right.
For a certain fixed amount of time to give them the pi phase shift, then it's...
Yeah, I think that's exactly right, John. Yeah.
So it just seems strange that they're making these statements.
It's good, isn't it?
Yes. Okay, so we should thank Peter again, and